Well, oh, got to stay here. Thanks, Susan, very much for that kind introduction. And thanks, everybody, for coming out. I'm going to do things in the reverse order just because I probably forget otherwise. So I'm just going to mention briefly what the course is about, and then basically what I'm going to talk today about is just a little piece of the course. So I'm going to teach a course called Cosmic Origins, and it's really about how everything formed. People have wondered about that, of course, since time immemorial, and they've made up tons of stories about it. We are in a privileged generation today, the first generation of humans who can actually watch all that stuff happening. And so I will talk, not in theory, but in visuals, about how stars are made, how planets are made, the galaxies, the universe. And it's an ambitious syllabus to get through in 6 weeks, but we'll try. And I will explain a little bit about the science behind these things, but today I'm going to mostly just work with pictures. So my title, just want to be very clear, A Star is Born. I mean like a real star, like the ones in the sky. How are they made? Where do they come from? And the story that I'm going to tell you about is really the story of our sun, along with all the other stars. And when I talk about planets in the course, you'll basically hear how the Earth was formed as well. So how does it start? This is a picture of the Milky Way at night, seen from the Earth. And if you get a good view of the Milky Way in the summer in a dark place, you'll notice that it's a band of light, but it's got all this dark lanes in it. And that is what we call in astronomy dust. It's really more like cigarette smoke. It's extremely small particles of things like silicon and carbon and so on. And those particles come from actually dying stars. So the galaxy is also a recycling scheme in which stars produce this dust. It goes out in the interstellar medium, and then it's used again to make new stars and planets. So in a process that we're not completely sure about, that dust sometimes gathers up into what we call clouds. I'll try to remember to give you scales on these pictures because the scales vary a great deal. This would be a few light years across. So these are large clouds. It looks very dark. It's much better vacuum in that cloud than you can produce in a vacuum chamber on the Earth. So the reason it looks dark is that there's sort of light years worth of this tiny dust that's extremely spread out. So it's interstellar space is basically a vacuum, but it's got a little bit of stuff in it, and sometimes it adds up to something you can really see. This is more typical. Here you just see part of the Milky Way, and you just notice that there's stars missing there. They're missing because they're blocked by this dust. So if you get a better view of one of these clouds, like if it's lit up by some hot stars nearby, this is a very nice Hubble picture of what we call a molecular cloud. And those are the sites of star formation. So the interstellar medium is very diffuse, but as I said, through a process we're not fully sure about, it sometimes collects into clouds. And here's one of those clouds, seen more close up. You can see that it looks like stuff's coming off of it. The clouds do not last forever. Astronomical timescales, of course, are not anything like human timescales. So when I say molecular clouds don't live very long, I mean they last for 10 or 20 million years. So here's one of those clouds. You can see it's sort of evaporating. That's entirely really due to certain hot stars are nearby, and they're essentially boiling off the surface. Inside that cloud, though, new stars are forming. This is where it happens. So the cloud is turbulent. Parts of it are a little more dense than other parts, and sometimes they get dense enough that gravity can actually collapse that part of the cloud, and that's when we start making stars. So here are two views of another molecular cloud, also from the Hubble Space Telescope. This is in visible light, basically, and this is in infrared light. These dust particles are kind of the same wavelength as infrared light, so we can actually see through the dust in the infrared. And that's part of the reason we're able to peer into these molecular clouds and actually see the early stages of star formation. I'm going to talk about this later, but I just want to point out up here, that's got a funny little head with two, I don't know, horns maybe, and actually a little shock wave here. There's a new star forming inside that little knot there, and the star is producing those jets of material. I'll show you more about that later. But there are a lot of other places in this molecular cloud which we can see in the infrared where stars are also forming. So some of these little dots here are new stars inside the cloud that are just forming. How long does it take to form stars? Not that long, like 1 million years. Very short in astronomical timescales. And it's beautiful. These are another couple shots. But what happens is the actual act of forming stars is detrimental to the cloud. So the stars form, they start shining, they shoot these jets of material out, they cause more and more turbulence. If there are massive stars in there, they produce a tremendous amount of radiation, and basically the cloud gets destroyed by the process of star formation in 10 or 20 million years. So here's a new cluster of hot stars, and you can see the cloud is being cleared away around them, and you can see that parts of it are being very heated by these stars, and so basically the whole process goes through in about 10 or 20 million years. You end up with stars. Sometimes they're in a nice cluster like this. More often they're just sort of there, and then they spread out over time. And so our sun was probably formed in a cluster which then dissolved later. So there are presumably siblings of the sun scattered through the galaxy. We're going to actually look for some with this new satellite that we have, but we don't know of any right now. So here's a piece of a cloud that's just being boiled away, the last parts of it. Okay, this is the constellation of Ryan. For those of you who go out and look at the sky ever, it's up now. So this is a winter constellation. The constellation itself is these 4 bright stars here, shoulders and legs of Orion. This is the famous belt, those 3 stars in a row. And then if you have a dark sky, you can see the sword hanging below that. In the middle of the sword there is the Orion Nebula. That's the nearest major star-forming region to us. It's about 1,500 light years away. There are some closer ones, but Orion is the largest nearby star-forming region. Here you can see it. This is the same part of the sky here, now seen in the infrared. So in the infrared is kind of heat radiation. So the stars heat up the dust, and they glow in the infrared. So if you take an infrared picture, the sky looks quite different than it does in visible light. Of course, almost all these stars you don't see from Lafayette here. The city lights are too bright. But if you go to a very, very dark place, you'd see many of these. But if you could see in the infrared, the sky would look quite different. So now you can see the interstellar medium in this area has got lots of clouds. This is the Orion star formation region. And what I'm going to do for the next few slides is zoom in there. Not in theory, but with actual images. So there's the sword of Orion. Now we zoom out on that, and you see this glowing cloud of gas. That's actually the tip of a molecular cloud, and it's being lit up by stars that formed there recently, and it makes this nice nebula, which is a current site of star formation. So the stars that are lighting it up were formed in the last few million years. They're not going to last more than a few million years themselves because they're high-mass stars. And there are about 2,000 low-mass stars are also forming in that same region. We can see them in the infrared. So if we zoom in on the nebula here and just look at this part and don't make it so overexposed, you can see these 4 bright stars. They're the ones that are lighting up the nebula. And we're going to zoom in on that area there. So here are the four. They're called the trapezium because they make a trapezoid. And now you can see the surface of the molecular cloud behind them. So they've evacuated the cloud right in their region. They're still shining in on this cloud where lots of stars are forming behind it. And I'll point out this little object here. You see it looks like a kind of comet, sort of. There's a glowing tip and a dark thing behind it. So let's zoom in on some of those. Well, here, this is just the trapezium. Let's go one more in. So here's one of these things. And now we need the Hubble telescope to see this. These are tiny little things in the sky, but it's actually pretty big. So what you're looking at here is a new star forming. You can't actually see the star. This little blue thing here is actually a disk of gas and dust around the star. The star is buried in there. And the gas that was making the star is being blown by these hot guys back this way. So it's like a windsock. So there is actually a stream of fast particles from the bright stars, and they're blowing on the little knot that was making this new star and blowing it out into a windsock. But inside there is a little disk of gas and dust. So this is about the size of our solar system, that little thing there. It's like 2 or 3 times bigger than our solar system, but that kind of size. So here's a bunch of them that are in the Orion Nebula. These are the ones you can see just on the outside. There are a ton of them inside that you have to see in the infrared. But if you look, they have, here you can actually see the star in the middle there. Mostly you see disks. There's that one we were looking at before. Here's one interesting. There's the disk, that dark sausage-like object this way. We're seeing it edge on, and the star inside is just lighting up the inside there, so you can see that little light from the star buried in there. And this one is actually one that you're looking face on into, so you see the star in the center of the disk, and the little dark circle around it is the disk of gas and dust. Why do we care so much about these disks? Well, that's how you make planets. So our solar system is laid out in a disk. You know, the zodiac, that's the plane in which all the planets travel. That's because they were all made inside one of these disks. So they're all in a plane. And that's why we have the constellation, the path of the planets, the zodiac. In the course, I'll talk a little bit more about the physics that is hidden behind this. Why do we get disks? It has to do with angular momentum, but I'm not going to talk about it here. This is an actual picture of a disk seen edge on. So the disk is actually here, and then there's a cavity on both sides of it that's being lit up by the star that's in the middle, and that's what this is here. And then there's this jet coming straight out the pole on both sides, and they are powered. I'll explain how they work in the course. But basically, they're powered partly by the star itself. The star has a magnetic field, and it's able to launch this jet. And what you're seeing is basically the part of the cloud that's collapsing into the star, kind of collapses from all sides originally. But then the star starts clearing the middle with its own jet, and actually the disk also has a wind flowing off of it for the similar reasons. And so they clear out this cavity in the middle of the cloud that's coming in. So you actually have material flowing in from the sides, so that would be in here, and flowing out along the poles. So you get inflow and outflow at the same time, and a central disk, which is where you're going to make planets. And in the middle of that disk is the star. And the disk is there, well, I'll explain why later in the course. This doesn't show up quite as well as this is a picture of one of those disks. You can't unfortunately see it quite. There's the dark lane here. That's the shadow of the disk, so the star's light is blocked there. And here you're looking into one of those bowl bowl-like cavities. And there's one on the other side too, which you can barely see there. You probably can't see it. We're getting pictures at this level of detail. This is actually almost better than the Hubble, using a new technique called interferometry, where you combine the light from several telescopes and they act like they were pieces of a much bigger telescope and give you even more detail. So I'll talk a little bit about how that works. This was done at the Europeans' array of 4 8-meter telescopes. So part of the reason we're seeing star formation so well is our instruments keep getting better and better. I just like this picture because it's beautiful. So this is this region here blown up over here. So again, there's a molecular cloud in here, the surface of which is being lit up by a star there. And here, there's a new star forming. You can see a little bit of the disk here, and you can see that jet firing out. And then it's plowing into the cloud and making this shock wave here. And you can see the opposite shock wave over there. So just very cool. This is the scale here is a couple of light years again. So the star is really launching into the cloud on the scale of light years, and that's why it tears up the clouds after a while. Here's an even better one. This is called the lightsaber picture taken by Hubble. So again, there's a new star forming there, and here are the 2 jets and the cavities being cleared out in the cloud. There's actually another one here. In an earlier part of star formation, the disk itself launches broad jets in both directions, and you can actually see one here. This is a jet coming off of a disk of an even younger star. So remember, all of this goes on in less than 1 million years, but something like 1 million years, a few 100,000 years, after which the star manages to clear away the stuff around it and stops getting built up. So, as I'll explain in the course, it's hard to avoid this particular scenario for making stars. You almost always get a disk around it. It almost always launches these jets, and the disk then concentrates all this dust into a plane where it gets dense enough that you can make planets. And in the last few years, we have been able to make a census of planets or get a statistical idea how many planets there are out there. So I now can say, for the first time since my 40 years of teaching, this is just always happens, just about. Most stars have planets. Planets, for a long time, we wondered how many other planets are there. Then we learned how stars are made. We say, oh, gee, there are a lot of disks. There are probably a lot of planets. And then in the last decade or so, we were able to confirm, yes, indeed, there are a lot of planets. It's a natural part of star formation, and it's the natural site for planet formation. And just to sort of finish up here, you can do this, as I said, more easily. You can see through the dust better in the infrared and even longer wavelengths of light, like microwaves and even the radio part of the spectrum. And there's this fancy new array of, they're not radio telescopes exactly, they're more like microwave telescopes. I guess they could see your microwave oven. And they're in an array like this in the same way that I talked about earlier. So there's a bunch of them, and they're spread out. They're all in Chile, on the Atacama Desert at about 16,000 feet, where you're above most of the water vapor that would block their view. And they combine the light from all those, they all point at the same direction, and they combine their light in a way that gives you even higher resolution. And this is a survey now of disks around young stars seen by this ALMA array. And you can see there's all kinds of disks. A bunch of them seem to show rings and gaps in them. And that's, we think, an even more direct view of planets. Planets would form these rings and gaps in the disks. So now we can actually see that, sure enough, many of the disks appear to be forming planets. Here's sort of the ALMA poster child. One of the young stars I used to study when we were just starting to learn about star formation. Had no idea that we were looking at this, but actually the star has a nice disk around it, and the disk has a whole bunch of rings in it. And those may well all be due to planets forming in that star as it forms. And I think, yep, that's all I wanted to say about star formation here. But if you come to the course, I will explain in more detail why this happens, what the physics behind it is, a little bit. No equations, just descriptions. And what we'll see is that when you make galaxies, a lot of the same stuff happens. So you may recognize this sort of could be a picture of the Milky Way galaxy too. And the similar processes go on very different scales in astronomy. And then the last part of the course will be on the Big Bang and the whole universe, which doesn't look like this, but has given us the situation where this goes on all the time everywhere. So I'm going to stop there, and I've been told I can take a few questions, so I will do that. Yeah.
In your course, what kind of materials do you post?
Yeah, so I will have a PowerPoint presentation for each lecture that will get posted internally to the OLLI site. And then there's an online intro astronomy book that's free that is available to you, and I have in the syllabus, I have the sort of chapters you can read in there to support the material. So if you want to do it in more detail, you can do it through that book. Yeah.
What creates the rotation of stars and planets?
Yeah. Right. So that's a great question. That's the sort of thing I'll go into more detail with. I'll just tell. Oh, I'm sorry. Yeah. So his question was why is it all spinning like that, and why does it make a disk? So the answer is, at the scale of the molecular cloud, which is light years across, I said it was turbulent. So the gas is moving this way and that way, and it collides sometimes and makes a knot that will collapse to make these stars. Well, it's almost impossible to make that knot so that it's totally standing still, right? It's going to be turning somewhere or another because it was turbulent. The turbulence that made it doesn't turn much. The typical rotation time for one of these knots that's going to make a star is a few million years. So it's turning very slowly. But now we're going to take it from the size of a light year down to the size of the solar system, which is only a few light hours across, or try to make a star, which is only a couple of light seconds across. So I'm collapsing by a factor of 10 million. And so if you remember how skaters work, right, the skater will be spinning slowly and then pull his or her arms in and start spinning faster. Well, imagine they shrunk 10 million times. They'd be really moving a lot faster. And that's what's going on here. In fact, this disk is formed because there's too much spin, actually. The particles out here are in orbit around the star, so they can't get any closer because they're already in orbit. And this is the size of this. The orbit of Pluto would be inside this inner circle. Okay? So actually, star formation turned out to be a big problem. How do you get rid of all that spin? And the disk turns out to be one way to get rid of it, and those jets turn out to be another way to get rid of it. And so nature solves this. The problem is not how do you get it spinning. The problem is how do you get rid of that spin so you can actually make an object as small as a solar system, and especially as small as a star. So those rapid pointy jets that I was talking about, those are the solution to the problem near the star. Basically, they're taking away all the spin, and the star is just dumping it like crazy through a mechanism I'll describe. Yeah?
Can you talk a bit about the temperature of these molecular clouds, and how does it change as it's going towards the formation of stars?
Right. So the temperature in the, let's see, I think I can probably jump quickly back. Maybe not. Let's Yeah. Now let's use this picture. So the temperature in the outer parts of this thing are, now you know about absolute zero, right? So the temperature in this room in the Kelvin scale, in which zero is absolute zero, temperature in this room here is about 270 degrees, okay? The temperature here is about 20 degrees. So it's much colder than liquid nitrogen or anything like that. It is warmer than liquid helium, but not by much. Okay, so it's very cold in these molecular clouds. Partly because as soon as you go into the cloud, you can't see the stars anymore on the outside, and so it just gets very cold in there. Now, as it collapses towards making a star, it'll then begin to heat up. One of the things that we can talk about in the course is release of gravitational potential energy. So as the thing is collapsing, it is actually releasing energy, and that will heat it up. So by the time we get to that disk I was showing, you might be up to a few hundred degrees in the inner part of few hundred Kelvin, so warmer than room temperature by now, in the interior of the disk near the star. And of course, once the star starts shining, well, it's a star, right? So its surface is a few thousand Kelvin, and it'll start heating up the disk that can see it to those kinds of temperatures. So there's a huge range of temperatures, right? Anywhere from tens of Kelvin to thousands of Kelvin, depending on where you're talking about. Yes?
Some of these images, the molecular cloud has a sharp edge. Why is it so sharp rather than diffuse?
Yeah, well, of course, this is a little bit like the sun, too. The sun has a sharp edge, right? Yeah, not really, though, but, it's a ball of gas. It looks sharp. Well, it's like clouds, the clouds, like especially the puffy ones, they look like they have really sharp edges, but you go up next to them, it's just fog. Well, no, it's due to the fact that that you're looking at a diffuse object, but it goes from being sort of opaque to transparent in a small fraction of the size of the object. So then you say, oh, that looks like a sharp edge. So it's not really sharp, but yeah, it looks sharp. And why is it ending? It's ending because the molecular cloud, well, it's called a molecular cloud because the atoms are cold enough that they can form molecules. When you go to the outside of the cloud, all the rest of the stars are shining on it. They have a lot of ultraviolet light. They break up the molecules. So essentially what you're seeing is the surface to which starlight is able to penetrate and break up the molecules. And once you're inside enough, it can't do that anymore. And so that makes a kind of a sharp edge. Remember, this thing is light years across. So the edge might be, hundreds of times the size of the solar system thick, and it would look sharp on this scale. Yeah.
Are most of the photographs here from Hubble?
A number of them are. This one is, for example. Some of them, the more detailed ones, were from these new interferometers. So we're able to now take sharper pictures from the ground than Hubble can with a few fancy techniques that I'll say something about. But
Well, I had a question about the James Webb Telescope.
oh yes,
Is that like the next big thing in telescopes, the James Webb?
yes, that'll be the next big thing in space telescopes. So that's 3 times the diameter of Hubble. It's going to mostly work in the infrared. You've already heard some reasons why we might want to look in the infrared rather than the visible.
Well, I had one more question, and that's, I've heard various things about James Webb. Is it on schedule to be completed?
So the schedule for James Webb keeps moving. So it's always on schedule. But it moved again a few months ago to 2020, late 2020 or early 2021. It had been right about now. I really don't have anything else to say about it except it's an incredibly complex project. In my opinion, there are way too many eggs in that basket at this point. But so it's a 6-meter telescope, but it's in pieces, like the big telescopes that well, actually not like the ones I was showing, but like most big telescopes these days. So it's a bunch of hexagonal pieces of the mirror. They have to unfold themselves and get in place properly. Then, because it's in the infrared, you don't want the telescope itself to be warm. So it has this huge sunshade that also has to unfold, right? So you got to put all this into a rocket cone, send it up beyond the moon, actually, in this case, and then get it to all unfold properly with no glitches. So there's a thing that's, I don't know, it's bigger than this room, that's a shade for the telescope that keeps the telescope in the dark all the time. And that has to work properly, and then the telescope has to unfold properly, and then all the instruments have to work. And there's no repair missions out where it's going. So I think everybody's really nervous, and that's one reason it keeps slipping, because they want to really make sure it's going to work. So they keep checking stuff. Maybe one last question. Or maybe we ran out of questions. No. Yeah.
Gibor, do you want to weigh in on the controversy around SETI, around reaching out?
Oh. Okay. The question is, there's been recently an argument in the community that listens for signals from intelligent civilizations around other planets. A part of that community says, well, why don't we send some messages too? And another part of the community says, you have no idea who's listening or what they're going to do with that message. Let's not do it. My opinion on that is too late, guys. The Earth has been broadcasting its presence for 60 or 70 years. What's interesting is our primary, our most easily detected intelligent signal is from the radar arrays that the U.S. and the Soviet Union had to watch for each other's nuclear missiles. Those were very powerful, very narrow frequency radio signals that we didn't find any missiles, but we sure sent out a lot of signals. But even beyond that, all our TV and everything is leaking off into space. So I'm not sure it matters whether we send messages or not, because we already are, basically. And then who's listening? Well, let's hope nobody's listening that's not nice. Yeah.